Hey there, chemists. Welcome back. We are going to keep talking about carboxylic acid derivatives. We started off with just carboxylic acids, and today we're going to start to look at the derivatives of these compounds, namely the acid chloride. We already know how to make them. We make them from carboxylic acids, and we'll see there's a lot of things we can do with them by doing substitution reactions of some nucleophile, replacing, in this case, a chlorine. I want to start off with just a couple of reactions we already know, and then we're going to move into some newer ones and do a few mechanisms. So we already learned how to make carboxylic acid chlorides from the acid. That's using thionyl chloride, SOCl2, plus the acid. We actually saw in Orgo 1 that if you react an acid chloride with a Grignard, such as RMgX, it will add two equivalents of that nucleophilic carbon source. Unlike ketones and aldehydes, the addition occurs twice. And then below that, we can add a source of hydride with lithium aluminum hydride. Similar mechanism to the Grignard addition, it turns out. Two equivalents of hydride will add. What if you only want one equivalent to add? That's what this reaction is up here. Again, from Orgo 1, using a cuprate, R2CuLi, will form the ketone, as opposed to a tertiary alcohol down there. And right below that, I actually have an Orgo 2 reaction from a few units ago. This is also an acid chloride to a ketone, but specifically a aromatic ketone. I was trying to remind everybody that we learned the Friedel-Crafts acylation reaction. In this case, with just benzene and aluminum chloride, you get this benzylic ketone. And below that is actually a new one. This is to make an anhydride. We haven't learned anhydride chemistry yet, but we will. That's the next lesson. You make them from acid chlorides and carboxylic acids. Until you lose an equivalent of HCl. We actually saw that mechanism in the previous lesson, or one of the previous lessons. Just there it is as a reminder. Okay, so now let's look at some modifications of these, some applications of these, and even a new reaction here and there. Starting with how to take an acid chloride and turn it into an ester. You do this by just reacting with an alcohol. So let me redraw that acid chloride. Acid chlorides are very electrophilic. They get attacked at the carbonyl carbon. You can imagine why or understand why because of that electron withdrawing oxygen and the electron withdrawing chlorine. So this is a very electrophilic carbon. That means that my alcohol is going to be a nucleophile, will attack the carbonyl carbon. The electrons go up to the oxygen. Notice the chlorine does not leave directly. We get an intermediate. Chlorine is still attached. There's our, what used to be alcohol, directly attached, new carbon-oxygen bond. And in classic acyl substitution chemistry, the oxygen donates its electrons back, so draw an arrow reforming the pi bond, and the chlorine can leave. We actually saw this a little bit in Orgo 1, where we looked at how nucleophiles like Grignards attack acid chlorides. So you generate another intermediate, and your chlorine or chloride leaving group. Looking at the product to make the ester, we're just one step away. We need to remove that extra H on the oxygen. I'm going to use the chloride to do that. And this shows how you not only make your ester, but an equivalent of HCl. This can happen with alcohols, this can happen with acids, this can even just happen with water. So acid chlorides are very reactive. They often can react with just moisture in the air. And you know this if you're ever in a laboratory and you open a bottle of an acid chloride, you'll see fuming HCl quite frequently if it's humid enough in the atmosphere. Okay, next up, how about turning the acid chloride into an amide? It's actually a very similar mechanism to the one up above. I want you to hit pause and see if you can go through the arrow pushing for how an amine reacts with an acid chloride to make that amide. Try that now. Okay, let's see how you did. Redraw that acid chloride. And when the amine sees this, it nucleophilically hits the carbonyl carbon. The electrons go up to the oxygen. You get a very similar intermediate to what we saw in the previous example. New carbon-nitrogen bond, two H's and an R group still attached. Now I have a negative on the oxygen and a positive on the nitrogen. And what goes up must come down. So take a pair of electrons from the oxygen, bring them back to form a pi bond, and kick out the chlorine. You get an intermediate. Still have a positively charged nitrogen with a chloride, and the chloride will take one of those H's, neutralizing your amide. And what you generate, again, is an equivalent of HCl. Now, unlike the previous example, we're actually not done. There's one more extra step here. We just formed a strong acid, HCl, and you're in the presence of a good weak base, in this case the amine, and the fastest reaction in the world is going to happen. You're going to have an acid-base reaction where the amine reacts with the HCl, so you get an ammonium, RNH3 plus and Cl minus. So we consumed a second equivalent of our amine to do this, which means if you want to make an amide from an acid chloride, go back up to the top and modify this and say 2 equivalents. You're going to consume a second equivalent of that amine. You can't stop it because of that acid-base reaction that happens at the very end. We'll see there's other ways to make amides from other acid derivatives where you don't have to use 2 equivalents, but in this example, in this kind of reaction, you do. Okay, the last one on your lesson for today is going to introduce a new reagent. This is abbreviated dibal. And let me start off by showing you what dibal looks like, and then we'll see how it reacts. Dibal stands for di-isobutyl aluminum hydride. It looks like this. It's an aluminum with a hydrogen, and it has 2 what are called isobutyl groups attached. And it acts as a mild hydride, a mild source of H-. That's simply because of these sterically crowding isobutyl groups. And you'll notice you form an aldehyde, which normally reacts with sources of hydride, but not in this case. If this reaction is done successfully, the hydride will not react with the aldehyde. It will react with acid chlorides. In fact, we'll see that this reagent takes any acid chloride and can turn it into the aldehyde. That's not why it's called dibal, but I often remember al, and it makes me think of aldehyde, and dibal usually makes aldehydes from these acid chloride derivatives. Let's see how it works. Redraw that acid chloride. I'm going to abbreviate dibal as just H negative. And like all the reactions we've seen today, it nucleophilically attacks the carbonyl carbon. The electrons go up. You get an intermediate, a negatively charged oxygen. And then we reform the carbonyl, bring a pair of electrons back from the oxygen, and kick out the chloride. And you're done. There's your aldehyde. You kick out a chloride that will coordinate with some counter ion from the reagent in the reaction. Okay, so that's a summary of how acid chlorides react, some reactions from earlier this semester in Orgo 1, and a few mechanisms to illustrate some new ones. Next up, we'll talk about esters and anhydrides, and then beyond that, the rest of the acid derivatives. Thanks for watching.